Hey everybody, so in this video I'm going to be talking specifically about what Bayes' rule is, what it means and how it might be used. In the next videos I'm going to be explaining how we can justify Bayes' rule, how we can think about it in a lot of different ways. But the important part of this video is just understanding what is the point of Bayes' rule, what sort of information is it utilizing, and what sort of information is it able to give you. So for that, let's go ahead and jump right in. I'll share my screen. So Bayes' rule is this theorem right here. And what I'm going to be doing in this lecture series is explaining three different ways in which we can try to understand how Bayes' rule has come to be, or how we've justified Bayes' rule. But to start off with, we need to understand just first, what does it say? So to do that, let's break down all the different pieces of this big, ugly theorem that you might have seen in textbooks. So first off, Bayes' rule is often cashed out in A's and B's or H's and E's. The specific letters that we're using here don't matter too much, but I like to use H and E when we're first explaining this, because the idea is H is supposed to stand for your hypothesis on a particular question. So maybe your hypothesis is, I wonder if I'm sick, or I suppose that I'm sick. How confident are we in this hypothesis is going to be our ultimate question. And E is supposed to represent our evidence, or one way we can think about it is representing evidence. So the idea is, suppose E represents the statement, I received a positive test for a disease, right? I took a COVID test and it comes back positive or something like that. And the question ultimately that we're interested in is this good or strong evidence for the claim that, yes, you are sick? Or more specifically, how good is the evidence for the hypothesis? That's ultimately what we're interested in. So before we dig into the details a little further, this term out front here, which is usually, or oftentimes you can think about that as like what we're solving for, this is basically going to be asking, how likely is my evidence, or how likely is my hypothesis now that I've seen a certain amount of evidence? So that's going to be ultimately the question we're interested in, is how likely is my hypothesis based on new evidence? But we still haven't explained all the technical pieces of how this language works. What's the P, what's this V bar? So this is just the intuitive idea. So let's get to those nitty-gritty details though. So when I wrap parentheses around a capital letter like H or E, and I put a P next to it, so we typically only use P not to stand for any sentence, but just to indicate that I want to talk about a probability of something. So if I put a P and wrap parentheses around a particular letter, I'm asking, what is the probability of the sentence that's referring to? And we can think about this as a percentage between 0 and 1. So if I'm interested in P of H, I'm looking at the probability that H is true. So this is how confident you are, ignoring evidence. So we don't have any evidence yet. We're ignoring the E. So what is your confidence that you are sick without considering evidence, right? Without considering the E. So this is what we call the prior probability. This is how confident are you when you start out that your hypothesis is true. So is it 25% likely that you're sick? Is it 33% likely that you're sick? Is it 0.0001% likely that you're sick? And so the idea, right, is that this number just gives us an indication of how likely it is that your hypothesis is true. And we can think about that as either a subjective, like how confident are you that this thing is going to be true, or you can think about this in just an objective sense about how likely is it, on average of 100 people, how many of them are actually sick, right? And so as we add on more of these nuts and bolts, so if I put an exclamation mark next to a letter, this is known as a bang symbol, and it just means not. So it's also known as a negation or a not symbol, and it just means if I say bang H or something like that, I'm just saying H is false, right? So if I say not H, I'm saying that H is false, and so it is false that I am sick. My hypothesis is false. So not H would just be the statement, I am not sick. So P of not H is the probability that H is false, right? What's the probability that I'm not sick? And intuitively, so this is the sort of thing we could justify or explain in more depth in a session that's focused on probability and the foundations. But intuitively, we can see that if I'm looking for the probability that something doesn't happen, that's just 1 minus the probability that it does happen, right? So if I'm looking at what's the probability that I'm sick, that's just 100% minus the probability that I'm not sick. So if there's a 15% chance that I'm not sick, the probability that I am sick, right, is going to be 85%. Okay, or so say you have a biased coin and it's 33% chance likely to go heads. Well, we all know very easily, very quickly, then that means there's a 1 minus 33% chance that it goes tails, right? There's a 66% likelihood that it goes tails. So this rule here, we won't be digging into it any further, but the idea is we just have this, it's a very intuitive rule about how if there's a certain likelihood of something happen, the likelihood that that thing doesn't happen is just 1 minus it. It's called the complement. Okay, so let's keep going with our nuts and bolts. So now we have the exclamation mark explained and all of that, and we also have P explained, but we haven't explained this vertical bar here, which occurs numerous times in Bayes' formula. So what does that vertical bar mean? All that means is the word given, right? So we can just think about this as what is the probability of something given that, or assuming that, or if you were already told that something else happened. So what's the probability that I'm sick? So we'll get to this in just a second. What's the probability that I'm sick given that, or if you tell me that I received a positive test? So if this is probability of A given B, it's what's the probability that A is true given that you know B is true, or if you were to assume that B was true first. So this is what it means to say we're going to conditionalize on a piece of information. We're going to say, now suppose we have more information, how likely is it that the thing I'm interested in is true? So whereas before I was just interested in the probability of H, now I'm interested in the probability of H, assuming that I see a positive test. So the real heart of Bayes' rule is going to be about thinking, what's the difference between where I started, my prior probability, and where I ended up, which is called my posterior probability. So there's how confident am I that I'm sick? Just, okay, maybe I'm like 1% sure that I'm sick because 1 out of 100 adults in my community have this particular disease. And then I say, well, now assuming, conditionalizing, if you give me this new evidence that, hey, no, you're not just a random adult in this community, just, any old adult. You're a random adult that has a positive test. So conditionalizing on that information, now how likely is it that I'm sick? So the probability of H, so this right here is the probability that H is true, given that he is true. Assuming that he is true, right? If he were true, how likely would it be that H is true? If you see a positive test, now how likely are you to be sick? Are you now 100% sure you're sick? Are you not, did you not change your estimate at all? Did it lower? Did it lower a little bit? Did it raise a little bit? Exactly how much should your estimate change? And that's what Bayes' rule is going to allow us to do. It's going to allow us to figure out this thing right here, the probability of my hypothesis, assuming this new evidence. Okay, so that's what we have with this given, with this conditional language here, probability of something if we assume this new piece of information. And right, we can look at this in the opposite ways too, right? So what's the probability that you see the evidence you do if you were actually sick, right? The probability that you actually see a positive test rate or a positive test, assuming that if you were right about the hypothesis, right? So suppose you actually were sick. How likely is it that the evidence comes back and says, yes, you're sick, or that the test comes back positive, right? This is what we call a true positive success rate. If you send 100 sick people into the testing center, how many of them are going to come back and say, yep, you are actually sick? All of them will be sick, but only 99 of them will receive a positive result, right? That's the true positive rate. How many of our positive results are in fact those for sick people? On the flip side, we can look at this false positive rate, right? So suppose you had 100 healthy people, right? We're saying, what's the probability that you get a positive test, assuming that this person was not sick, right? So you send a not sick person in and you ask, what's the likelihood that they receive a positive test? So one way we can think about this is send 100 healthy people in and ask how many of them are still going to come back with positive tests, right? Any positive test for a healthy person, that's called a false positive. So it's important not to think of H here as healthy. H is our hypothesis, right? And our hypothesis is that you're sick. So sorry for the confusion there, but that's inherent to any sort of formal language. You're going to start getting slipped up with what the words mean if you don't stay clear. But the idea here is, what's the likelihood that I see a positive result, right? That the thing says, yes, you have COVID, even though I fed it a healthy person. I fed it somebody that's not sick, right? And that's what we call our false positive rate. And so what Bayes' rule does is it allows us to come from, if we feed it in, so we can ignore the second way of writing Bayes' rule for a moment, it's going to turn out to be exactly the same, but I think it's less enlightening than this one before. But if we already know, all right, how confident were you to start off with that you're sick, right? We have our prior, and you also know what's your true positive success rate, right? Like, how often do healthy people get positive results? And then you also know the opposite, right? You also know how likely am I that I'm not sick, right? Which is just 1 minus this number for how likely am I that I'm sick. And then you also know the false positive. What Bayes' rule does is it essentially lets you to flip these conditional probabilities, right? We know the probability of if you're healthy or if you're not sick, what's the likelihood of giving certain evidence? And what we're able to determine is, all right, now, based on getting a certain amount of evidence, how likely is it that you're sick? So what we know to begin with, and often how these problems are given, is what we're given to begin with is, all right, how often do we have true positives? How often do we have false positives? And what was your prior, right? You're often given these 3 pieces of information. And as a result, if you know these 3 pieces of information, your true positive, your false positive, and your prior, you're able to determine, okay, now how likely am I in my hypothesis based on my evidence? So these things are just going to be facts about the treatment itself, right? So anytime you take a certain test, you should be aware of how often is this test wrong, either as right, how often is it right? How often are the positives correct? How often are the positives incorrect? Equivalently, you could cash this out if you were given other information too. Like if you were given just the true negative rate and the false negative rate, we could work out a similar sort of thing. But the idea is, so we can approach this in a number of different ways. But the idea, and the important thing to grasp, to understand what's going on here, is that what Bayes' rule is interested in doing is starting off with the pieces of information like this, your prior probability, the true success, or the true positive rate, the false positive rate. And from those, you're essentially able to flip around the conditional probability. And so that lets you say, see, okay, how likely is my hypothesis given the evidence that I've seen? All right, let's look at an example in order to tie all this together. Okay, So Bayes' rule, we can think about it, right, as most of these questions, or often these questions, are going to give you three pieces of information. We can think about the prior that we start with. Hey, there's only 1 out of 1,000 people that are, or 1 out of 10,000 people that are sick. We can look at the false or the true positive rate. So, right, so out of 100 people that are actually sick, 99 of them are going to get results that say, yep, you're sick. And one of them is going to get a result that says, no, you're not actually sick, even though they in fact are. And then we also might be given the false positive rate. So out of all the people that are not sick, the amount of people that are not sick, 2 out of every 100 healthy people are still going to get a positive test result. So again, these are the sorts of pieces of information that are generally, or depending on the circumstance and context, will hopefully be available to you, right? So if you go and you look at specific COVID tests or something like that, or if you're interested in different medical situations, or whether or not your paint has lead in it or anything like that, or if you are interested in taking a birth test or something like that, or a pregnancy test, these are all the sorts of things that will have true positive and false positive rates. And if you're getting it from any sort of reputable source, these sorts of things should be published, right? And should be very accessible. Because as we'll learn, depending on what these true positive and false positive rates are, that dictates how much you should change your opinion based on this evidence. So in this case, suppose only 1 out of every 10,000 people has a particular sickness. And 1 out of every 100 sick people still comes back, hey, with an erroneous test that says you're not actually sick. And 2 out of every not sick people come back with an erroneous test saying that you actually are sick. So it's not a perfect test, but we can say, generally speaking, it seems to be giving us the right answers for these 2 occasions. Sometimes it gets it wrong, but for most of these 2 groups of people, it seems to be getting it right. So how much, if I get a positive test back, how much should I adjust my opinion, my expected likelihood of being sick based on that test? So what is the likelihood that I'm sick given that I receive a positive test? So, well, all we have to do is plug in each of these pieces of information into our formula, and it gives us exactly the answer. The probability that you're sick, given that you've seen this test, is just equal to your prior times the true positive, divided by the prior times the true positive, and right, what we call the complement of the prior times the false positive. Now I know that seems like a lot of bloated lingo, but like those were just the 4 or so terms that we defined above, right? We have our prior, we have our true positive, and we have our false positive. And then we also have the complement of our prior. So once we plug in all those things, then getting the answer is actually pretty trivial, right? We just plug that into a calculator and we can see, oh, look at that. The number comes out to be 0.49. So what does this mean? So, right, we're saying that the probability that your hypothesis is true, given this particular amount of evidence, is 0.49. So that means now that you have that evidence, right, you're not 100% sure that you're sick. Right, then the answer would have had to be just 1. It would have to be, right, 1.0 or 100%. But right now you're nearly 50% sure that you're sick. There's a 50 or a 49 just about likelihood that you're sick. So it's almost a flip of a coin whether or not you're sick. So, and at this point, now that we've gotten through all this mathematical stuff, it's important, I think, especially from thinking about it in terms of someone that's trying to adjust their opinions and use this as an evidence updating scheme. Let's realize what's going on here. Let's try to think, okay, was this actually good evidence or not, right? Before I had my prior, and now I have my posterior, which is based on now including more evidence. So now I get to ask, all right, how much did that evidence move the needle, right? So before I started off with a 0.01% chance of being sick, and now I'm at a 0.49. So on the one hand, you might say, well, that's pretty weak evidence. You might say, well, shoot, I'm still more confident than not that I'm actually healthy, right? If this was your pregnancy test, you would still think it's more likely than not that I'm not pregnant still, or it's more likely than not that I don't have COVID, or whatever the test may be, because there's still a bigger number, right? The probability that H is not true is still higher. Right? There's still more like a 51% chance that the opposite is true. So you might think, oh, well, then this sounds like bad evidence, right? It's not pushing me, over the fence to thinking it's more likely than not that I'm sick. So why would I think this is strong evidence? Well, remember where we started from. You started with thinking there was a 0.01% chance, so a 0.0001 chance of finding. So let me also do this, of finding the right answer, right? But now we're learning, so there's not just a 0.01% chance of finding the right answer now, or of being sick. Now you have a 49% chance of being sick. That is many orders of magnitude bigger, right? You've gone from thinking, oh, I'm only one out of 1,000 people like me would be sick. Now, 1 out of 2 people like you are sick. You have drastically changed your opinion concerning the likelihood of this hypothesis now. So what this highlights is an important aspect of using Bayes' rule, that saying something is good evidence or not is never a cut and dry thing. It's always a matter of, well, what sort of problem are you trying to solve? What context? How does the context dictate which sorts of figures actually matter, or what sort of size of figures actually matter? So in this case, if this was me trying to figure out if I had some terminal disease, or if I was pregnant or something like that, I would definitely take this test very seriously. But I would also definitely take another test right away, because right, that's how we continue to increase our confidence in a particular hypothesis. As we take more tests, we continue to conditionalize on more evidence. But one thing I won't do is consider any specific test just conclusive, or just solving the issue. So Bayesianism in general, and philosophers who call themselves Bayesians, very much like to just sit in the world of credences and just move their confidence up and down, and resist, many of them do at least, ever just committing to a full-blown claim like, yes, obviously this hypothesis is true, or something like that. Now, we're getting more into the more nitty-gritty details, or the philosophical questions surrounding Bayes' rule, and what differentiates people that approach this from different mathematical backgrounds. But the point here is that what we're concerned with is this growth, or this change. And this is something that everybody appreciates, that what matters is not just the absolute value at the end of the day. What matters is, when you're considering how good of evidence you have, what matters is the change from your prior to your posterior. And if you can understand that dynamic of what's going on in Bayes' rule, you should have a very good sense of what's the point of using Bayes' rule in this way. Okay, in the next video, I will be explaining why Bayes' rule actually works, and how do we actually get this formula. So far, we've only just plugged in the numbers and understood what the terms mean, but it'll be very useful and very instructive to actually walk through how do we get to Bayes' rule. So join me again for that video, and I'll see you then.